If we do it after this, if we do it before the stop, it will take more time.
Yeah, right. Yeah, that's much better. Oh wait, people can come in late a little bit. So this is a brand new computer here. I've seen them before.
But the personal was not time. The memory, the hard disk is really small. There is no flash can carry several. Only one PHP.
Oh, it doesn't even have a firewire. If it had a firewire, I might do it. Yeah. Isn't there one that doesn't have a hard drive at all?
Yeah, it doesn't. No. It has drive, but it's smaller.
Okay. I remember when I read about it at first. I thought they had another
model
one.
which costs 1,000 francs a month, which has a new solid state
Flash memory. Yeah. I think if I did a lot of traveling, I could see doing that because it's probably durable. Yeah. I don't think I'll offend anybody. Thanks, man. Looks like I'll start almost 5 minutes late, but not quite.
All right, welcome to this morning session. So the first talk is by Steve Gubser, who's going to speak on the gauge string duality and QCD at finite temperature.
The mic is live. Well, I'd like to first thank the organizers for giving me the opportunity to speak, and also to thank the CERN staff for all their hard work. This is aimed at being a review talk. I beg your pardon? This is aimed at being a review talk of a field that certainly has many practitioners. And my list of topics has some significant omissions. Fortunately, one of them will be corrected very soon by Shiraz Manwala's talk. But let me just start with the most basic context. We'll be talking almost throughout about the near extremal D3 brane metric and its limits and things probing that metric. And in the now familiar strong coupling limit, in which the gauge string duality is most tractable, there was a calculation by Igor Klebanov, Amanda Pete, and myself. Oh, pardon me, that's this one. And later a calculation by Igor Klebanov, Arkady Tsaitlin, and myself, where we computed the free energy and found that it was 3/4 of the free field result, with some correction that depended on the 't Hooft coupling of the Super-Yang-Mills theory in such a way that it seemed to be interpolating toward the free field result as you go back to weak coupling. Furthermore, there have been several papers calculating from the other side, from the side of small 't Hooft coupling, what the free energy is. And at least this first term has the right sign to interpolate in the other direction toward the strong coupling result. Well, a group of nuclear theorists have given the most modern presentation of this topic, which is interesting already, that they're doing string theory as well as nuclear physics. They found that these two expressions, because they involve only lambda and lambda to the 3/2, if we look once more, lambda to the 3/2 here, and then a linear term in lambda, they scratched their heads a little bit and thought, aha, there is a simple pad-A approximate, which is uniquely specified by having these two formulas, this number 4 and the number 3 before it, as appropriate limits at large and small elliptic coupling. They don't make any claim that this is an exact result. The only reason they pick this pad-A parametrization is the one that I already stated. It matches the limits known to the accuracy known. So they graph for us here various approximations or guesses to the interpolation function of free energy divided by free field free energy. And these pad-A curves correspond to this guess, and then they had another slightly different pad-A parameterization that is only slightly different numerically. So you can see that the perturbative results converge quite badly. Here's just the linear term, zooming down like this. And here is the linear term plus the next to leading order, or next to leading order correction. And so indeed, the perturbation series here is doing quite badly, even at lambda of 1/2. They, however, have developed, in the context of QCD, a hard thermal loops approximation, which is roughly speaking to the perturbation theory, supplemented by some gap equations. And this seems to be a tried and true means of extending perturbation theory, again, in the context of QCD. So they tried it for n equals 4, and they were pleased to find that their hard thermal loops approximation works rather well up to quite a respectable value of lambda, and only gradually drifts away from the supposed near exact answer, the pad-A approximates. All right, so that's already, let's say, a theoretical interface between nuclear physics and string theory. But the whole game really got rolling with these papers by Policastro, Sohn, and Sterinetz, later by Kovton, Sohn, and Sterinetz, and by other authors, including Bushel and Liu, Herzog, and frankly more than I can remember, calculating the ratio of shear viscosity to entropy density. And just to make sure I don't leave any specifics out, shear viscosity enters relativistic hydrodynamics most simply as the first derivative correction to the standard ideal fluid dynamics constitutive relations. So here we have energy density, here we have pressure, here we have the local form momentum of the fluid, here we have the metric, Minkowski metric in flat space, and here we have a projector. This projector picks out the spatial parts of the metric in the local rest frame. And so this slight monstrosity here asks in the local rest frame, what is the shear of this flow, this flow specified by a 4-vector u beta? And then this term multiplied by the bulk viscosity zeta is a rather simpler thing. It just asks how much expansion is there in the flow. It's literally the spatial dot product del dot u in the rest frame. All right, so the bottom line is that after all the dust has settled, it has settled, eta over s also has some lambda to the 3/2 correction with a notably large coefficient, numerically large. So this 1 over 4 pi is quickly corrected as you go toward, as you go away from very strong coupling. And I would point out as well that in more generic string theories, you might expect these corrections enter with a lower power of lambda, because after all, type 2b is rather special in having only an alpha prime cubed correction. Nevertheless, this has been a real touchstone of strong coupling physics in relation to experiment, because, well, let's say for starters, Harvey Meyer in 2007 did a calculation of 8 over s in pure glue on the lattice, and he found a result conspicuously close to the 1 over 4 pi result. Conspicuously close, let's say, compared to perturbation theory, which might give you results 10 times as big. However, he puts large error bars on his result. This is his best result, but when he is pressed for 90% confidence level, he gives this, which you can see is quite a bit bigger and more in line with perturbation theory. These lattice computations are notoriously difficult because you have to get at eta from a real-time correlator, and to get a real-time correlator, you have to do some kind of Wick rotation. So let's run through this a little more. I've got Zeta trotting along with us because I'll eventually want to talk about bulk viscosity. In n equals 4 superunit mils, it vanishes on account of conformal invariance, but let's just bring it along for the ride. So, the Green's functions of interest are the retarded Green's functions of spatial components of the stress tensor. So now what we're imagining is a static fluid where the rest frame, the local rest frame is everywhere the same. And we just take correlators of the space parts of the energy momentum tensor corresponding to little deformations of the fluid in any direction you please. And by Kubo's formula, the infrared limit of these Green's functions gives you the shear and bulk viscosity with some tensor structure which is inevitable. Okay, but as I was saying, this is something you can't access directly from the lattice. What you can access is the Euclidean Green's function, which is calculated only at discretely many Matsubarro frequencies. Furthermore, you discretize both time and space, so you only get finitely many evaluations, approximate evaluations of this function. In order to get back to what you want, which is the omega equals 0 limit of the retarded correlator, you have to parameterize this Euclidean Green's function in terms of some spectral representation. And because you only have finitely many approximate evaluations of the Euclidean Green's function, you have to make assumptions about the spectral weight. So that's to convey this is hard work, and that's why Meyer is very conservative in his estimates. Still, I think he's probably being a bit too conservative, and optimistically, pure glue will have eta over s rather close to that of superunit mils. I should have said this is pure glue near the transition temperature, so at a strongly coupled point. All right, now let's talk about experiment. The reason experimentalists got all excited about this is that they can measure something called elliptic flow. The geometry of elliptic flow is three-dimensional, so let me give you two views. This is the side view where you have heavy ions colliding with some impact parameter. And here is the end-on view, or the beam's eye view, where, okay, we have some ellipsoidal or almond-shaped region of overlap. And these parts that don't overlap, they are essentially spectators to the collision, so they go down the beam pipe. And what's left is this, this almond-shaped region. And the idea of elliptic flow is that there's some approximately constant pressure in the red region and then zero pressure in the white region. So evidently, there is a larger pressure gradient horizontally than vertically, just by approximating the derivative by delta p over delta x. You can see that must be true. So there will be preferential expansion in the horizontal directions. And this anisotropic expansion, of course, is something that they can measure rather well. So now let's look at data. This is data from the STAR experiment, and what we're looking at is what I've indicated here. Sorry about all the notation. PT is the transverse momentum to the beam pipe. Y is the rapidity, defined like so, and phi is this azimuthal angle. So the dependence on phi is all we really care about. Well, not quite. And you make some expansion in multipoles, if you like, and the first D wave contribution is the one that they really can track the best by far. And this is what it looks like as a function of PT. So long before eta over S, Rick phenomenologists were expert with ideal fluid dynamics, and they recognized very early that this V2 could be reproduced rather well with ideal hydro. This solid line is ideal hydro. And Derek-Tini, some 5 years ago, showed that the ideal hydro curves are very quickly knocked down by even a small amount of shear viscosity. So this gamma S is an attenuation length of sound, and tau naught is a characteristic expansion, but this is a good translation. This ratio is numerically similar to this ratio. All right, so the string theory result, or the strong coupling result, might be the dashed line, and already it's below the data. However, it should be noted from Tini's paper that ideal hydro has been trained to do the best ideal hydro can against the data. For instance, initial conditions have been assumed such that there is an appropriate magnitude for the elliptic flow under conditions of ideal hydro. My eye suggests that if a slightly larger anisotropy were assumed at the outset, the 0.1 curve would drift up and match rather better than ideal hydro. But I'm not a professional. At any rate, what the professionals say is that data favors 8 over S in some range approximately like this. And it's indeed amusing that the string theory result for strong coupling is right in this range, and Harvey-Meyer's lattice results are too. All right, so moving on, let me talk about a series of further developments. One is the equation of state. So this is something studied for 20 years in finite temperature lattice QCD, and here's a sort of status report for 3-flavor QCD, up-down strange. And the first thing I notice with pleasure is that the plateau here is something like 20% below the free field estimate. I admit this is not first me who noticed this by any means, but it does remind me of the 3/4 factor. And Rick operates where? Somewhere around here. So, right in the plateau region. It's really lovely. And LHC will operate somewhere around here, close to the last data point on this curve. It drifts up through asymptotic freedom toward the free field result extraordinarily slowly. So a student, Abhinav Nalor, and I decided, why don't we study this equation of state with a bottom-up approach in ADS? Namely, why don't we give ourselves a little more freedom than n = 4 offers by introducing one scalar and one scalar potential. And the freedom comes from being able to adjust this function. So with a function to play with, we should be able to match one pre-specified function, namely the speed of sound as a function of temperature. And we played with one thing and another thing, and eventually, well, rather quickly found that a very simple potential, something of this form, will reproduce equation of state remarkably closely to what I showed you from the lattice. Another group in Paris, Gubser and Kritzis and collaborators, had a similar approach in which they not only got equations of state which were at least somewhat reasonable, but also logarithmic running of the coupling in the ultraviolet and a linear blue ball mass spectrum. Well, it's not that special to say we can reproduce a function given another function. But what we thought would be fun afterwards would be to see what that whole setup had to say about the bulk viscosity. So I remind you this Kubo formula. Now it has to do with the retarded-Green's function of the trace of the energy momentum tensor. Originally, I wrote it as the spatial trace of the energy momentum tensor. There is no difference between taking the spatial trace and the entire Minkowski trace when you're doing it under this omega to 0 limit. So in order to calculate zeta, we just start with our setup as specified in equation 15, and then we drop some mixture of a graviton and the scalar into the black hole horizon, and we ask about the absorption probability, and from that absorption probability out will come some value of the bulk viscosity. And because we fixed all our freedom from comparing to the equation of state, well, we should have some at least reasonable estimate of bulk viscosity. Because there is a mixing between the scalar and the metric, the equations of perturbation are a little bit complicated, but they simplify quite a bit in the gauge where the scalar is assumed not to vary. So that is a gauge choice that is possible when you pick spatial k equals 0. Anyway, in that gauge choice, everything becomes simple again. You have some single differential equation you're supposed to solve. This is straightforward work. And here's what you get. First of all, upper right is equation of state. The black squares are lattice, very similar to the previous plot that I showed you. And, well, by design, our curve comes very close to this lattice curve and could be made even closer if we allowed ourselves to adjust TC freely. Instead, we chose some prescription for TC. Okay, so here's equation of state, and then here is bulk viscosity. So the thing to focus on, let's say, is the red circles. This is the string theory computation. So bulk viscosity does rise near TC, but not very much. This 0.05 is less than eta over S. And now you might be wondering, why do I care so much about bulk viscosity if it's always small? Well, it's because the heavy ion community, well, more particularly Dmitry Karzev and Tuchin and Karsh and collaborators, proposed a hadronization scenario which relies upon having large bulk viscosity at the transition. So let me tell you just a bit about their idea and why I think our string theory calculations challenge it. They would like for expansion of the plasma to cause a large increase of entropy right near TC. And this large increase in entropy is associated with the production of soft particles and might explain why there's, well, so many particles that come out of a RIC collision. However, our calculations suggest that it's hard to get such a dramatic effect as this, because to get this, you need, well, singular behavior of zeta over S, or at least very, very large behavior right near TC. So, nice idea, but we think it can't work. Okay, so let me move on now, instead of talking about soft physics, to talking about hard probes. This is work by Herzog, Kazkaz, Karch, Kovtun, and Yaffe, and also by myself. And there was a related paper by Casaldri, Solana, and Tini. And the bottom line is very easy to state. If you have a heavy quark moving through a thermal medium that's strongly coupled, like n equals 4 supergram mils, then the rate at which it loses momentum is proportional to the momentum itself. we did this calculation, or at least I did it, in the limit of large mass. So this ratio here, which is really P over M for any finite mass, is better expressed in terms of the velocity of the quark, V, in this formal limit of infinite mass. So even though P is infinite in this limit, dp dt is finite. All right, so the way this goes is that a quark on the boundary of ADS trails out a string behind it, and the string probes the ADS Schwarzschild geometry, and it assumes some simple analytical shape, which I think I will not show you, and if you will, it scrapes against the horizon and loses energy and loses momentum. The way that I did the calculation was just to calculate the momentum flow down the string world sheet. So this calculation of the drag force is evidently closely related to the static quark-antiquark potential, and I'll return to that, that analogy soon. All right, so if you pass to finite mass, then you can estimate the stopping time or stopping distance of a heavy quark. And now we're interested in putting in numbers. Well, in order to put in numbers, what I think one should do is first think about the quark-antiquark potential, because that's something that's rather well understood from lattice calculations. What the lattice people do is they put a quark and antiquark at fixed positions, and then they do another Euclidean path integral calculation on a computer, and they find an excess free energy of this quark-antiquark configuration as a function of radius. So FQQ bar is the excess free energy. And then they pick out some effective alpha strong as a function of both R and T. And this derivative knocks out any constant terms from the excess free energy, and the 3/4 factor is a color factor, which I don't want to explain in detail. All right, so what the lattice people give, or what the lattice people get, is some alpha strong which falls off with radius, and this fall off you should think of as Debye screening. If the radius is more than about a femtometer, then Debye screening is much more powerful than confinement when you're above TC. If you were below TC, if you were in the confining regime, let's say 0 temperature, then alpha strong would rise and rise and rise because of confinement. So in order to make what I consider to be a good comparison between string theory and lattice, it seems to me one should try to get the string theory quark-antiquark potential to at least approximately pass through the lattice points as best it can. As best it can means that what we can do really is calculate the quark-antiquark potential from this shape. From the massless exchange, only a little bit of work has been done, and maybe if we could do it better, we would get a string theory curve that would functionally fit this Debye screening form over a larger range of R. And I haven't been explicit, but I also favor comparing n = 4 and lattice at fixed energy density rather than fixed temperature. All right, so this is my preferred prescription, and I will use it consistently in this talk for comparing n = 4 and QCD. However, there are alternatives, for instance, to set the tree level couplings equal and to compare at fixed temperature. Again, let's look at data. What I'm plotting, or what the Phoenix people are plotting, up here is their famous RAA ratio, the nuclear modification factor. And this thing has a messy definition, but let me just tell you the crude definition. RAA as a function of PT is the percentage of charm quarks escaping the medium with a given transverse momentum. So it should never be greater than 1 with that definition. You can see it's almost never greater than 1. And what happens, what's interesting, is that it zooms down to 0.2 or even maybe a bit below, and behaves very much like light quarks do. The light quark RAA factor is something like this. So that extra heavy mass of the quark, which perturbative QCD would suggest prevents it from slowing down much, doesn't seem to help the charm quark escape. Charm flows, according to the jargon of RIC physicists. And then there's some more details of this histogram, which I won't bother you with too much, but only say that this Phoenix data, when compared to theory, matches best some calculations by Van Hees, Greco, and Rapp, the pink region. And their stopping distance is roughly double what I would get with my preferred comparison. So, could have been better, but we, after all, are comparing two very different things, n equals 4, supernomials, and QCD. There are some other proposals, notably by Vorinen and Tini, which make a comparison in such a way that this number comes out just right, but since I knew the number, one wonders. Anyway, this is, I think, a respectable success. But something might be more dramatic, especially as the LHC comes into the game. You remember that there was a dependence on of the stopping time of the reciprocal mass. So the B quark time is longer by a factor mb divided by m charm, and roughly speaking, this percentage should scale as the ratio of stopping times. So there's a study by Horowitz and Giulassi, pardon me, where they propose that this double ratio of what charm quarks do versus what B quarks do should be a distinctive separator between perturbative phenomenology and strongly coupled phenomenology. And so what they've done here is to say, oh, the ADS-CFT result is pretty much this ratio down here, and then the perturbative QCD result doesn't care that much about the difference in mass between C and B, especially as you go up and up and up in transverse momentum. And their various curves here correspond to varying assumptions about the medium. They relate to initial conditions and total multiplicities. And there are some related studies by Theodore Brassavianu and David Denteri. This is a nice study, but what I'd point out with some concern is that it's hard to know when ADS-CFT will stop working and perturbative QCD will turn on. They've tried to make some estimates of when that happens, and the estimates correspond to these circles and bars. So what I would expect is that, assuming strongly coupled phenomenology is the right thing, is that you'll get some persistence of a low value, and then it'll head up at some PT. So that is the best I would hope for, but it may still be a distinctive signal. I think in view of time, I'm going to skip stochastic forces and go on to another hard probe phenomenon. Let's start with the data. When you have a hard scatter, what can happen is that one quark can get out of the medium without interacting much with it if the hard scatter occurs close to the edge. And the other result of the hard scattering would then typically have to plow its way through a great deal of medium. So these histograms relate to what happened to the green thing. You trigger off of the red parton, or the jet that it creates, and its direction sets a definite value of the azimuthal angle. Relative to that angle, you ask what came out at various delta phi's. So delta phi is the azimuthal separation between the trigger hadron and then some other hadron that came out as a consequence of the green parton. Well, that's not quite accurate, because what could happen is that two hard hadrons will be part of the same jet. So when you see this peak near delta phi equals 0, it's because of ordinary jet physics in vacuum. But when you see this big humpy structure over here at delta phi equals pi, that is plausibly the result of a parton plowing its way through the medium. And this double hump structure is what they mean by jet splitting. It should have been another peak like this. It is another peak like that when you're talking about proton-proton collisions. So the splitting of that jet into this double hump structure is actually a fascinating and unexpected and still unexplained phenomenon. So what does string theory say about it? We can go back to this picture of a quark moving through the plasma. Well, I'd rather do a light quark for you, but it's harder. So I'll stick with heavy quarks. And you can ask, what is the response of the medium to this heavy quark? We've already seen what the response of the quark is. It slows down. But it must dump its energy in some pattern, and we want to know what the pattern is. So in principle, this is a simple calculation. We just want to know the VEV of, or the expectation value of the stress tensor. And we calculate it by allowing a graviton to propagate to the boundary. The details get to be somewhat obnoxious, and so I will skip them all and just quote you results. In terms of a dimensionless position variable and a dimensionless version of the pointing vector, where I've also included some factors of the 't Hooft coupling and the Lorentz gamma factor. So here it is. Capital X equals 5, you can think of as being a femtometer. So there's some distinctive flow that has a little bit of a vortex here. Oops, going the other way. It has what's called a diffusion wake, a stream of plasma behind the quark. And it has a sonic boom. And for a while, I thought, oh, gee, this sonic boom is going to be the key to the story. But according to a recent phenomenological study by Gilles Assy and Barbara Betts and Jorge Naroña, it's really this region within a femtometer of the quark, which is the most interesting because the flow is the strongest. So what they did is they performed an isochronous Cooper-Frye hadronization on this flow, and what they found with appropriate PT cuts is that it does produce a very distinctive double hump structure. Remember, this is for heavy quarks, but I think it should be encouraging to us that perturbative QCD simply does not give a double hump structure. And it is so difficult to get double hump structures that theorists are constantly asking experimentalists, are you sure you did this right? And experimentalists are saying the data is the data. So this seems to be perhaps a real window of opportunity for strong coupling physics to say something distinctively different and possibly really right. But stay tuned. I think the question is not settled, and there are some problems, as I've noted in this list. I think I'm really running short on time. I have 10 minutes, right? 15? Oh, good. All right, in that case, let me try to pass on to the case of light quarks. And the first thing to mention is the well-established perturbative phenomenology that energy loss from radiative processes scales not linearly with distance traveled, but quadratically. It is an interference phenomenon. And let me not go into it, but just refer you to the original literature and perhaps especially the more accessible work of Wiedemann that came a little later. This Q-hat parameter, the jet quenching parameter, is the rate at which the quark receives transverse momentum kicks. So it's kind of like me trying to drive through the construction region near Quentin Airport. Every time I go through, I get a random kick in my momentum and never wind up going the same way. But in heavy ion physics, what's been proposed by Wiedemann and Kovner is to calculate this Q-hat parameter via a partially light-like Wilson loop, as I've drawn, in the limit where the spatial separation L is much less than the distance traveled x. And this proposal puts it within the purview of ADS-CFT. And so this calculation of Liu, Rajagopal, and Biedermann comes from the straightforward prescription for Wilson loops. Well, perhaps not wholly straightforward. Before I get to the caveats, let me quote the numbers. What they find is that Q hat is 2.3 GeV squared over femtometers. That's not the numerical result that they quoted in their first paper, but I think it's the most reasonable take numerically on their results, because I would set T of 280 MeV, which is about right for Rick, people think, and I've included a factor of square root of entropy, which they advocated in a later paper. So 2.3 GeV squared over femtometers. Obviously, it is rather sensitive to temperature, so it could go quite a bit up if you raise the temperature even a little, as they point out. It's at least triple the size of the perturbative estimate, and that perturbative estimate is not under good control. So at least we start learning that jet quenching seems to be stronger according to a strongly coupled gauge theory. However, there are some criticisms of this calculation, in particular the choice of classical saddle point for the string that closes off that Wilson loop. And it seems to me that additional concerns are that Q hat as defined through the Wilson loop may not directly measure the rate of energy loss or of momentum diffusion. And when I compare it to calculations of momentum diffusion for heavy quarks, I don't seem to arrive. So I think there are some interesting unresolved puzzles here. But let's look at data. This RAA we've seen before. It's now the fraction of light quarks or gluons, hard to tell the difference, after hadronization. But the fraction of light objects that make it out of the thermal medium with a given PT. And you can see that there's this distinctive plateau at about 0.1617. Anyway, less than a fifth. And various calculations, theoretical calculations have been done, usually allowing Q hat to be a parameter. And one particular one that appears in the papers that I've quoted favors a value of Q hat of 13.2 GeV squared over femtometers. So even the n=4 calculation of Liu, Rajagopal, and Biedermann was not big enough. With Silviu Pufu and Daniel Gulata and Fabio Rocha, I decided to try to revisit this calculation, somewhat in the spirit of Alde and Maldasena's calculation, treating an off-shell gluon as a string that rises up off of the D3 branes, or rises up out of the depth of anti-de Sitter space and moves forward. But at finite temperature, something very distinctive happens. Where the string goes through the black hole horizon, it cannot move in ordinary killing time because of the infinite redshifting. It cannot move. So we have a falling chimney problem, sort of, or a falling string problem. You start the string off at some position with some profile of velocities as a function of depth, and then you let it propagate forward classically. It would be nice to conclude quantum corrections, but classical is hard enough. And it will take an infinite amount of time to fall wholly into the horizon, again, because of infinite redshifting. But it will only get a finite distance. So this is very much like the energy loss from jet quenching. And it seemed to us that there was an obvious calculation to do, given the initial energy of this string, what is the maximum distance that it can reach. And this maximum, well, it's going to, this delta x is going to vary according to how you distribute the energy over the string. Different profiles of v of y might give you different answers. But what we believe is that in the limit of large energy, there will be some approximate universality. Anyway, we made some estimates, and later authors, including Paul Chesler and Andreas Karch at the University of Washington, did some numerics that approximately bore us out. I'll say more in a minute. Numerically, what we found is that the distance traveled is approximately this cube root formula, where again I've rendered the position dimensionless and the energy dimensionless with the factors of the temperature. So that's what we get. And if we went back to, pardon me for a moment, if we went back to this BDMPS formula and solved for Q hat in terms of delta E and delta X, that would give us a formula like this number 37. And I call it a rough estimate because really jet quenching is a probabilistic phenomenon, and I'm treating it as sort of purely classical. So there's some significant caveats here. But within those caveats, what we arrive at from this falling string calculation is estimates of the jet quenching parameter, which are remarkably constant in energy. Remember that we had a slightly different scaling from the square root of E. We had cube root of E, but that's at large energies. And in the energy regime of interest, this function is quite flat. This Q hat dependence is quite flat. And it falls basically within the 3 sigma range of experiment. So that's nice. But I should emphasize that this is using my preferred comparison scheme of fixed energy density and a 't Hooft coupling of 5.5. So it's a good thing that we're treating gluons as significantly virtual because they are. They stop in a femtometer or 2 femtometers or some rather short distance. I've noted that it is questionable already to compute Q hat from that formula because we have a probabilistic phenomenon on the perturbative QCD side and classical phenomenon on string theory side. It's also bad that we don't understand the relation of our calculation to that of Liu, Rajagopal, and Wiedemann. But I think more could and should be done here, including to consider the graviton response and more numerics along the lines of Chelsler and Karch, who found a slightly larger delta X. And that, I think, is encouraging because it pushes Q hat down a little bit where it probably needs to go. How much time do I have? 5 minutes? All right. So let me finish by discussing once again soft physics. This is one of the first events seen by the star detector. And as you can see, heavy ion events are a real mess. But they can track 50,000 particles all at once. And it will be, I beg your pardon. They can track 5,000 charge tracks all at once in the star detector. It will be quite an interesting challenge to see if CMS and Atlas and Alice can track the rather larger number of particles that may come out of a heavy ion collision at LHC energies. So indeed, the question of the day is how many charged particles come out. This is related to the total entropy produced in the collision. It's related by a factor that, as I've indicated, of 7.5. This factor comes, for instance, from considering hadronization as a transition from quarks and gluons to a free gas of hadrons. And from the free gas of hadrons, you can compute S and N charged, and the ratio, the ratio is about 7.5. So this number, at least at RHIC energies, is rather well established. 38,000 units of entropy are created in a gold-gold collision. Well, when you see that number, you think to yourself, wouldn't it be nice to get that out of a black hole? Wouldn't it be natural? And so we tried. The way we tried was to assume that it's the conformal window, or the nearly conformal window of QCD that matters. And we took this ratio, which is all that will enter into our calculations. We took this ratio from lattice. So we don't even need to ask whether we're comparing at fixed energy or fixed temperature. We're just considering the ratio. And we did a Penrose-style trap surface calculation to figure out how large a horizon would be produced by a dual collision of gravitational shocks. Gravitational shocks means that we're replacing the heavy ion with some boosted conformal soliton. So by conformal soliton, I mean the holographic shadow of a point source, a gravitational point source, mapped onto the boundary. So whatever this thing is, whatever this shadow is, you know it's going to have power law tails. And in fact, the power law tails are 6th power tails. The exact form is what I've indicated here. It's a well-known result. So we're colliding two sort of mushy blobs with power law tails instead of two clean heavy ions. But still, let's try. We can at least control the size of these mushy blobs. The characteristic size of L should be matched perhaps to the RMS radius of a gold nucleus. So all parameters are fixed. We know the energy, it's the beam energy of the beam energy at Rick. We know L, we know the ratio epsilon over t to the 4th. And so we calculate some trapped surface and immediately read off a entropy. And what we get is 35,000. And that's a little shocking. It really worked. Or did it? Well, it might have been a bit of an accident that it worked as well as it did. Because what you see is that our energy dependence is the 2/3 power of the beam energy. And that's not good. Data favors the 1/2 power, as I'll show you in a minute. So it could be, I regret to say, that we had a little coincidence that right about at top Rick energies, these kind of calculations just work. And below them, they won't work as well. It's not too much of a tragedy because the trapped surface entropy is a lower bound on the total entropy produced. And so we wouldn't be in contradiction with data at lower energies where total multiplicity is measured. However, if the 1/2 scaling persists to higher energies, we'll be in the soup. That might be an indication that black hole methods work best right around top Rick energies. And that certainly is also reinforced by the success of eta over S and the other things that I've told you about. However, I'm hoping for a little better. I'm hoping that as you proceed to higher and higher energies, this trapped surface will start poking its head up into the region of ADS where we shouldn't be doing supergravity at all. Into the region of ADS, in short, where things are perturbative and little entropy is produced simply because the partons pass through one another. So the picture that I would like to believe is that most entropy production occurs in a range of energies dual to a range of depths in ADS where we can use a supergravity approximation. Now that's just optimism on my part, but let's assume I'm right. What would it mean? Well, that UV cutoff, where I literally cut off part of the trapped surface from my calculations, converts the e to the 2/3 scaling at large E to an e to the 1/3 scaling. So once again, for the last time, let's look at data. The e to the 1/2 scaling, as predicted by a 55-year-old model of Landau, is remarkably good over a large range of energy scales, but it just starts to seem to fail a little near top Rick energies. So if you squint, that point is below the curve. Chemical potential shouldn't be an issue at Rick, so that the dot dash line is not to be heated, I think. And proton-proton is dipping more. So as we go up to higher and higher energies, like at the LHC, I think we should be looking for a slower scaling of total multiplicity with energy. Maybe something like a 1/3 power for heavy ions. And to be extremely optimistic, I might guess that something like that scaling might happen for protons. So that's all I wanted to tell you. Let me just end with some kind of outlook. Of course, I think this is fun stuff, and in fact, the closest interface we have currently between string theory and modern experiment. And there are many successful comparisons, or semi-successful comparisons, many more than I've been able to tell you about. However, we're always plagued by the difficulty of translation between string theory and QCD. And I think that we are in danger of too often measuring our successes against prevailing interpretations of data rather than data itself. But at least we have a strongly coupled laboratory that complements perturbative QCD and may sometimes be closer to capturing the true dynamics of QCD in a strongly coupled regime. Thank you.
Questions?
ADS-CFT is a strong coupling. Jets in QCD are weak coupling phenomena. If you wouldn't have a weak ground coupling in QCD but a strong coupling, you wouldn't have jets, you would have tensions, you wouldn't have polyclinic powers. The Q-hat proposal we have takes this into account by eliminating from a particle energy loss mechanism only that part of the calculation which is a strong coupling phenomenon. It is in exactly that sense that the Q-hat calculations differ from the Dragon string calculations which you advocate. That is a comment. The second comment I made to you already a month ago in Spain, that is that when we calculated Q-hat, and I looked up our paper in the FISREF letter, we quote for the Q-hat from our calculations value of 4.5, 10, and 20 GeV squared per square, and not of 2.3 GeV squared per square.
Yes, thank you. As you recall, I emphasized that I was quoting results from your formulas that I felt personally were the most reasonable. And I think it is quite possible for reasonable people to disagree, especially given the sensitivity of Q-hat on temperature. Not to mention the difficulty of translation to QCD. As for the question of the spatial distribution, where you mentioned that in strong coupling you would expect hedgehogs or some uniform distribution of energy, I think the thing to do here is to calculate. I think it would be quite interesting to look at the stress energy shadow of the falling string. And my expectation, although I can't be certain until I calculate, my expectation is that it would be, to an extent, columnar. And that if you performed isochronous Cooper-Frye on it shortly after the main falling occurred, that you would in fact find a columnar structure. But these are only expectations, and I think the calculation is well worth doing.
So I think there have been quite a number of useful applications of the ideas of ADS-CFT in terms of the real QCD, but we have a critical understanding why they're related. In other words, how close are we to actually saying this negative force fluidity again, you know, it's working so well, and it's not just be naive with that observation.
Well, I would suggest that to the extent it works, it is evidence for universality in the dynamics of gauge theory. And already you can see that in lattice QCD. When people calculate with pure glue, which they do far better even now than with quarks, provided you rescale TC appropriately and let's say rescale the number of degrees of freedom, things like the equation of state come out very close, except for right at TC where there's maybe some first order transition rather than second order. And in other ways, pure glue calculations seem remarkably closely related to lattice calculations with quarks. So I think we don't have to look far to see some evidence of universality in
I
gauge
think
theory.
the evidence is good by a lot of things that we showed. My question is how much we have to read to understand them. Why? That's my question.
Well, that is a deep question. And I'm afraid I don't have a very good answer.
Are the records being done to address that? I mean, are people looking into why these are working?
For me, the question would have to be posed more crisply before before I would know exactly what to investigate.
Well,
I wish I knew better.
More precisely, suppose you try to break this in the context of a string theory and try to study specifically those examples and try to see how they apply to QCD. Are those being tried?
Certainly, to an extent, there are calculations, within the Sakai-Sugimoto model and other string theory constructions with less supersymmetry. And these bottom-up calculations that I described, where you start with some adjustable potential in ADS, perhaps also have their virtues. But it still feels to me like one is simply trying to meet in the middle. And the question of why it works, when it works, is a hard one to address.
Steve, in the beginning of your talk, you discussed the agreement of the energy and entropy density, right? And in the end of the talk, you were computing the entropy from a black hole picture. Given that you know the energy of the collision, can't you compute the entropy by just looking at those equilibrium entropy-energy relationships?
Well, the collision is a non-equilibrium process. So I think that, let's say, whatever black hole you form in ADS, it's going to be ringing hard. It's not at all like let's say, a spherically symmetric anti-de Sitter black hole at early times. So certainly the equilibrium equation of state is an important input, but I think there's more. You have to know something about the real-time dynamics. And that's what ADS-CFT offers that is so rare.
Perhaps the last question.
Yeah. One of the biggest open questions in big data is the very rapid thermalization, because again, this non-equilibrium process that you just discussed. Do you see any chance of attacking that constantly?
Yes, there have been several attempts. The one I know best is one that I did with Silke Kuku, Joshua Fries, and Georgios Mikula-Dragakis, where we asked about how the black hole rings down. And that's a quasi-normal mode calculation when the black hole is nearly spherical. And so within that spherical cow approximation, I'm going to say a rather shaky approximation, we estimate the thermalization time to be about 0.4 femtometers over C, which is a pleasant number because the hydro people favor 0.6 femtometers to 1 femtometer. Other authors, I'm afraid the names are escaping me, have tried other things involving flows that look a bit like Bjorkian flow. Shuriak is one. And they seem to arrive at similar estimates. The thermalization time from a strong coupling point of view is, if anything, shorter than phenomenologically desirable.
Okay. I fear we have to postpone further questions to the break, so thank you again.